Welcome viewers. In this video we'll see the energy stored in capacitor, energy density of the capacitor and the problem. First we will see energy stored in capacitor. So the parallel plate capacitor is shown in diagram. At one plate positive charge is available, another plate negative charge is available. The voltage is applied between the two plates. Right? The voltage is applied. What will happen? The voltage across the capacitor is V. The voltage will be developed. In the closed loop, the voltage across the capacitor will oppose the supply voltage. So we are giving the supply voltage V so that the voltage is developed across the plate. That voltage will oppose the supply voltage. Right? The voltage across the capacitor parallel plate will oppose the supply voltage. The work done by the source against the opposition of V is converted into energy. So there is a opposition between parallel plate voltage and supply voltage. So that will be now converted into energy. Right? So we know that potential is the work done per charge. So what is the potential? V equal to dW divided by dQ. The potential equal to work done per unit charge. From that dW equal to V into Q. Cross multiply these two. So the dW equal to V into dQ. But we know that Q equal to CV. From that V equal to Q by C. We will replace this V as Q by C. So dW equal to Q by C into dQ. So this work done is due to only small charge. So by integrating on both the side, we will get the total charge. dW equal to Q dQ divided by C. So we have one parallel plate capacitor, voltage is applied. Then the voltage will be developed across the parallel plate. That voltage will oppose the supply voltage. That is now converted into energy. That is nothing but dW divided by dQ. Work done by charge. So after simplification we got this value. This is only small charge and small work done. By integrating on both the sides with a limit, we will get the total work done, total energy stored. If the capacitor is initially uncharged and the process of charging continue until the charge Q is reached. That is, the capacitor is charged from 0 to Q, initially uncharged, and then it is charged to Q. Then the total work done will be, so we can integrate this both the side with a limit 0 to Q, because the capacitor is charging from 0 to Q. Now see this, integral dW equal to integral 0 to Q, Q dQ divided by C. Now it is integrated on both the side, the limit is applied. So integral dW equal to W. 1 by C is constant, so integral 0 to Q, Q into dQ. So W equal to 1 by C, the integral Q is nothing but Q square by 2. We need to substitute the limit 0 to Q. So what will happen? 1 by C into Q square by 2. So that Q square divided by 2C. The energy stored in the capacitor is Q square divided by 2C. By substituting this limit, Q is replaced, small q is replaced by capital Q. So that Q square divided by 2C. You take this equation number 1. This is one formula. Energy stored in capacitor, one formula. Q square divided by 2C. We will see another two formulas. We know that Q equal to CV. Now we are going to substitute Q equal to CV in the equation number 1. So that what is that? W equal to Q square divided by 2C. That is, Q square means C square V square divided by 2C. Right? This Q square is now replaced by C square and V square. So 1C got cancelled. So what we have? C V square divided by 2. So that is nothing but half CV square. Energy stored in capacitor, another formula is half CV square. This is a very standard formula. Half into capacitance plus voltage square, half CV square. This is second form is available. Now we'll go to the third form. Same thing, Q equal to CV. From that, C equal to Q by V. We are going to substitute in the equation 1 C. We are going to replace the C value by Q by V. Here we replace the Q value by CV. This Q is replaced here. In this third form, the C is replaced by QV. Right? So what we have? Q square divided by 2C. So that Q square divided by 2 into C is nothing but Q by V. So 1 Q square is there, here Q is there, 1 Q got cancelled. This V is available in the denominator, it will go to numerator. So QV divided by 2, that is half QV. That is the third form. Right? So we have 3 different formula available. According to the data, we can use any of this formula for the energy stored in capacitor. Q square divided by 2C or half CV square or half QV. 3 different formula available. Based on the data, we can use either any one of this formula. Now we'll see the energy density. What is energy density? Energy density is defined as the energy stored per unit volume. So always density mean either length, area or volume we are referring. Here we are referring the volume. Energy stored per unit volume is nothing but energy density. Right? So the energy stored in the capacitor. Just now we discussed the energy stored in capacitor. 3 different form available. We consider the one form, half CV square. We will take this form, half CV square. So this energy stored by volume is nothing but energy density. So first we started with the expression half CV square. But we know that the capacitance is nothing but A epsilon by D. Area into epsilon divided by distance. Right? Now substitute the C, replace this C by this value, A epsilon by D. So half A epsilon by D into V square. For in order to get the volume, multiply and divide by the term length. So it will not, the originality will not affect. Multiply and divide by the term length. Right? Now we rewrite this 1 by 2 epsilon V square. This epsilon V square. Right? A into L divided by D into L. Right? So this L is written here. This L is multiplied with A. Right? So half epsilon V square divided by DL into A into L. Right? This L is available here. This L is available with multiplication of area. What is area into length? Area into length is nothing but volume. Area means 2 parameter, length and breadth, or length and height, or breadth and height. So breadth, height into length, 3 parameter. This is 2 parameter, this is third parameter. If 3 parameter if you multiply, that is volume. So what we have, energy stored equal to half epsilon V square divided by DL into volume. Right? Now bring this term volume in the denominator. Energy stored is denominator. So energy stored by volume equal to half epsilon V square divided by DL. Right? This volume is brought into denominator of left hand side. So what is this energy stored by volume? Energy stored by volume is nothing but energy density. That is half epsilon V square divided by DL. Right? Now we got the expression for energy density, that is half epsilon V square divided by DL. So based on this energy stored and energy density, we will see one problem. So we have parallel plate capacitor with 2 parallel square plate of area 50 centimeter into 50 centimeter. Right? The area is 50 centimeter into 50 centimeter, that is 50 into 50 10 to the power minus 4 meter square. By converting centimeter to meter, we need to multiply 10 to the power minus 2. Here 2 terms available. So that 10 to the power minus 4 meter square. Right? So the area is given. Separated at a distance 1 millimeter. The distance between the plate is 1 millimeter. That is 1 into 10 to the power minus 3 meter. It is charged with 500 voltage. The voltage will be 500. Then what we need to find? Work done in separating the plate from 1 millimeter to 3 millimeter. right? The distance between the plate is separated from 1 millimeter to 3 millimeter. So that we will take D1 as 1 millimeter, D2 as 3 millimeter, right? So 3 into 10 to the power minus 3. The epsilon naught is constant, 8.854 into 10 to the power minus 12. Then epsilon r equal to 1. We consider air medium. What we need to find? Work done. What is work done? Half CV square. The V is already available, but C value is not available. How will you find the C value? By using this data we can find. We will take this C1 and C2. If it is 1 millimeter, C1. If it is 3 millimeter, C2. So that is available here, C1 and C2. From C1 and C2 we will find the work done, WD1 and WD2. From that we can find the net work done, right? So we have the distance is 1 millimeter to 3 millimeter. So first we consider 1 millimeter. We can calculate C1 value. Then we will consider 3 millimeter. We can calculate C2 value, right? So that C1, C2. Using 1 millimeter, this will be using 3 millimeter. So A epsilon naught epsilon r divided by D1, 1 millimeter. So area is 50 into 50 10 to the power minus 4. Epsilon naught is 8.854 into 10 to the power minus 12 divided by this distance, 1 into 10 to the power minus 3. So C1 equal to 2.21 into 10 to the power minus 9 farad. By simplifying this we got this value. So when the distance between the plate is 1 millimeter, this is the capacitance value. When it is 3 millimeter, it will be C2. A epsilon naught epsilon r divided by D2. The area is 50 into 50 10 to the power minus 4. Epsilon naught is 8.854 into 10 to the power minus 12. The D2 value is now 3 millimeter. 3 into 10 to the power minus 3. By simplifying what we got, 7.37 into 10 to the power minus 10 farad. Right, now we got the C1 value and C2 value. By using this we can find what is the work done for C1, what is the work done for C2. The difference between that two will be the net work done, right? So I will find this work done now. So the work done WD1 equal to half C1 V square. Voltage is common, only C1 is there. So half into C1 we calculated, 2.21 into 10 to the power minus 9. The voltage is 500 voltage, 500 square. That is equal to, by simplifying this, 2.76 into 10 to the power minus 4 joule. Right? When the distance is 1 millimeter, this is the capacitance value, this is the work done. When the capacitance is C2, half C2 V square. When it is 3 millimeter, the capacitance value will be C2. For that, the work done will be half C2 V square. Half into C2 is 7.37 into 10 to the power minus 10 into 500 square. V square is 500 square. By simplifying what we got, 9.21 into 10 to the power minus 5 joules. Right? So this is the work done when it is 1 millimeter. This is the work done in 3 millimeter. Then what is the net work done? Difference between these two, WD1 minus WD2. We need to subtract these two values. So what we got, 1.83 into 10 to the power minus 4 joule. The net work done by moving the distance between the plate from 1 millimeter to 3 millimeter. This is the total work done. Net work done, 1.83 into 10 to the power minus 4 joules. So in this video we discussed the energy stored in capacitor, then followed by energy density, then one problem we discussed based on the energy density, energy stored.